Assalamualaikum and hello to everyone. So in this video tutorial, we will look at a question from subtopic 5.5, improving the cycle, Brayton cycle with reheating process. Okay, so we can read the question. So we have here a gas turbine, okay, generating set has a high pressure turbine where it is used to drive a compressor, and a low pressure turbine which drives a generator. So we have here two turbines, okay, so one high pressure turbine and one low pressure turbine. Okay, so when there is two turbines, so it has to involve a reheating process. Okay. Alright, so next is the air is drawn into the compressor at 100 kilopascal. So this is the pressure at the compressor inlet, and also temperature 25 degrees Celsius, the temperature at the compressor inlet. So the pressure after the compression, okay, and the high pressure turbine are 720 kilopascal. So this is the pressure after the compression process, and 400 kilopascal is the pressure after the expansion in the high pressure turbine. Okay, so respectively, the air leaves the combustion chamber at 1100 degrees Celsius. So after the first heating process, the temperature is 1100 degrees Celsius, and then reheated to 1100 degrees Celsius also. So after the reheating process, the temperature is also 1100 degrees Celsius. Okay, after the expansion in the high pressure turbine. So there is an isentropic efficiency for both of the turbines, which is at 85%, okay, or 0.85. So the question asks us to illustrate the diagram of the plant complete with a number on a TS diagram. So we have to sketch the TS diagram and we have to label the number of states. Okay. And then determine A, the cycle efficiency in units percentage. So this is the thermal efficiency for the Brayton cycle. And then the work ratio, RBW. And number 3 is the mass flow rate, M dot, when it is given the work net. Okay, so this is the work net in capital letters. Okay, so work net here is 6,500 kilowatts. So we have to find the mass flow rate. Okay, so these are the properties for air. Okay, so we can begin with step number 1. Okay, so step number 1 is to draw the schematic diagram. Okay, so we can try to draw. So we have here a compressor. Okay, so compressor here. Okay, which is connected to the high pressure turbine. So there is a shaft connecting the compressor to the high pressure turbine. Okay, which is also connected by a shaft to the low pressure turbine. Okay, low pressure turbine, and then the low pressure turbine will generate the work output to deliver power to the generator. Okay. Alright. So from the compressor, okay, so the exit of the compressor is connected to the heat exchanger for the heat addition process. So here it will be the primary heating, alright, number 1. And then exit, it enters the high pressure turbine for the first expansion process. Okay, so it exits. Okay, so we can draw either exit on top or exit below. So it exits the high pressure turbine and it enters a reheater. Okay, so it enters a reheater and it exits the reheater to enter the low pressure turbine. Okay, and exits the low pressure turbine to enter a second heat exchanger, okay, for the heat rejection process, Q out. Okay, so and then it exits the heat exchanger and enters the compressor again. Okay, so at the reheater also there will be a heat addition process, so this will be the Q reheat. Okay, so then we label the states. So inlet of the compressor is state 1, exit of the compressor is state 2, exit of the heat exchanger, inlet of the first turbine is state 3, exit of the first turbine, inlet of the reheater is state 4. Okay, exit of the reheater, inlet of the low pressure turbine is state 5. Exit of the low pressure turbine, inlet to the heat exchanger is state 6. Okay, so we have 6 states here. So this is the schematic diagram. Okay, not the TS diagram, but the schematic diagram. Okay, so this is step 1. So we know for the compressor is state 1 and 2. The first heat exchanger is state 2 and 3. The turbine, state 3 and 4. The reheating process, state 4 and 5. And then the low pressure turbine, state 5 and state 6. And finally, the second heat exchanger, state 6 and state 1. Okay, so we know which states are involved, okay, for the processes. Okay, so next is to come out with the step 2 is to come up with the equation. Okay, so step 2 is the equation. Okay, so for the first item, which is to find the thermal efficiency. So the thermal efficiency here, we know that the general equation is the work net, okay, in small letters, over the amount of heat added, okay, Q in. So there are two times, okay, there are the first primary heating and then there is the secondary heating, the reheating process. So the Q in here has to be Q in total, okay, because there are 2 times the heat addition process. Okay, so for work net, we can expand the equation. So work net, we know that it is the work output since there is 2 turbines, so there is the work out has to be the work out total. And since there is an isentropic efficiency, so it has to be the actual work out total. Okay, then minus the work input at the compressors, and it is the ideal work input because there is no isentropic efficiency. Okay, so this is the equation for work net. We can expand it further. Okay, so if we to expand it further, so work out total here, okay, is the first turbine, the work for the high pressure turbine plus the work for the low pressure turbine. So we can expand it further. So we have to write all the equations so we know which state is involved. So for the high pressure turbine, okay, it's CP, okay, state 3 and 4, so T3 minus T4A. Okay, for the low pressure turbine, CP, state 5 and state 6, T5 minus T6A. Okay, so for the work input, work input ideal is state 2 and state 1, so CP T2S minus T21. Okay, so we calculate individually the work output and also the work input, then we minus work output with work input, we can get the work net. Okay, for Q in total, okay, so for Q in total down here, alright, so for Q in total also it involves 2 times, so there is the Q primary or Q, okay, primary plus with the Q reheat. Okay, alright, so we can count it individually. So Q in, the first Q in, the Q in primary, okay. Alright, so it is state 3 and state 2, so CP T3 minus T2A. Okay, and for the Q reheat, okay, it is CP state 4 and 5, so CP T5 minus T4A. Okay, so because there is an isentropic efficiency at the turbine. Okay, so make sure your equations are correct. Okay, so this is the equations to find for the thermal efficiency. Okay, all the required equations. Okay, next is the back work ratio. So back work ratio is simply the amount of work input divided by the amount of work output. Okay, so we have calculated just now, so we just have to substitute it back. And then number 3 is the mass flow rate. So already given the work net in capital letters, which was 6,500. Okay, so work net is 6,500 kilowatt. Okay, so we know the equation for work net. Work net is also equals to m dot multiply with the work net in lowercase letters. Okay, so to find for mass flow rate, we just have to rearrange the equation. Okay, so m dot here is equal to capital work net divided by lowercase work net. Okay, so these are the equations which we are going to use to solve for the question. Alright, so next we proceed with step 3, okay, which is to find the required properties. Okay, so state 1. So state 1, we know the pressure. So P1 just now was 100 kilopascal, and the temperature in units Celsius was 25 degrees Celsius, but we have to plus with 273, so we can get 298 Kelvin. Okay, then we go to state 2. Alright, so state 2, the pressure was already given in the question. Okay, 720. Okay. Okay, and since there is no isentropic efficiency, so we have to find for the ideal condition only. So using the equation T2S minus over T21, okay, P2 over P1, K minus 1 over K. So we can calculate for T2S. Okay, so T1, P2 minus over P1, K minus 1 over K. So substituting the values, okay, I believe you can substitute the values. Okay, so we can get here 298, 720 divided by 100, 1.4 minus 1 over 1.4. So we can get here T to S equals to, okay, the ideal temperature here at state 2 is 524 Kelvin. Okay, next we go to state 3. Okay, so state 3 now. Okay, we have we know that the pressure is the same as pressure at state 2, so 720 kilopascal, and the temperature is already given 1100 degrees Celsius, but we have to plus with 273, so we can get 1373 Kelvin. Next is the state 4, okay, the first expansion process. So P4 is already given. Okay, if I'm not mistaken, P4 was 400 kilopascal. And there is an isentropic efficiency for the first turbine, which was 85%, okay, or 0.85. Okay, so at state 4 here, we have to solve for both ideal and actual condition. Okay, so we do for ideal condition first. Okay, so using the isentropic relationship equation for gases, okay, so 33 over T4S equals to P3 over P4, K minus 1 over K. Okay, so substituting the values, okay, so T3 was 1373, T4S, P3 was 720, P4 is 400. 1.4 minus 1 over 1.4, so we can calculate here T4S is equals to T4S, the ideal temperature at state 4 is 1161 Kelvin. Alright, next, since there is an isentropic efficiency, so we have to find for the actual condition. Okay, so using the isentropic equation, okay, for turbine. Okay, so for turbine, the isentropic equation is the actual work output over the ideal work output. Okay, so H3 minus H4A over H3 minus H4S. Okay, Cp T3 minus T4A over Cp T3 minus T4S. Okay, so the value 0.85. Okay, so the value 0.85 is equals to T3 minus T4A over T3 minus T4S. So substituting the values just now. Okay, T4A we want to calculate. T3. Okay, T4S 1161. So 0.85. So we can calculate for T4A. Okay, T4A here we can find the answer is 1193 Kelvin. Okay. Next will be state 5. So we proceed with state 5. Alright, pressure 5 is the same as pressure 4. So it's 400 kilopascal. And then the temperature after the reheating process is also 1100 degrees Celsius. So we have to plus with 273. So we can get the same, okay, as just now. And then finally state 6, which is after the second expansion process. The pressure P6 is the same as the first pressure. So it's 100 kilopascal. And also it has an isentropic efficiency of 85%. Okay, so the same as state 4 just now, we have to solve for the ideal condition first. Okay, so ideal condition first. Okay, so T5 over T6S, P5 over P6, K minus 1 over K. So we substitute the value. Okay, find for T6S. Okay, so 400 divided by 100, 1.4 minus 1. So here we can solve for T6S. Okay, so T6S here is equals to 924 Kelvin. Alright, so this is the ideal temperature at state 6, but since there is an isentropic efficiency, we have to solve for the actual condition. Okay, so same as state 4 just now. Okay, the isentropic efficiency for the turbine, the actual work output divided by the ideal work output. So it's H5 minus H6A over H5 minus H6S. Okay, so Cp T5 minus T6A over Cp T5 minus T6S. Okay, so the value is the same. Okay, so the value is the same. Okay, so 0.85 is equals to T5 was 1373. T6A we want to calculate. Okay, and T6S was 924. So solving this, we can get T6A equals to 991 Kelvin. Okay, so all the temperatures are calculated. So we can now proceed to step number 4. Okay, so step number 4 is just to substitute and solve. So for work net just now, the equation we know that the work net is equals to the work out total, the actual work out total minus the ideal work input. Okay, so we can calculate individually. Okay, so calculate individually. Alright, so calculate individually for work out and also work in. So work out total just now we know that it's the there's no dot. We are calculating in lowercase letters. Okay, so there are no dots in the equation. Okay, so we are calculating in lowercase letters. So for the first turbine, okay, for the first turbine, the high pressure turbine, okay, the high pressure turbine is we have already written the equations now. Cp T3 minus T4A. Okay, so substituting the values, okay. Substituting the values, okay, we can get for the first turbine 180.9 kilojoule per kg. For the second turbine, the low pressure turbine, the equation just now we have already written. Okay, substituting the values. Substituting the values, T6A was 991. Okay, so substituting values, the second turbine is 384. I've rounded up all the values. There might be some decimal points, but I have already round out the values. Okay, so we can find for workout total here. Right, so the workout total here. Okay, so we have to add both of these numbers here. So when we add both of the numbers, we can get, okay, we can get 564.9 kilojoules per kg. Okay, next we calculate the work input. Okay, the ideal work input was Cp T2S minus T1. So substituting the values. Okay, so T2S was 524. Okay, 524 minus 298. Okay, so we can get the ideal work input 227.13 kilojoules per kg. Okay, so we have the total work output, we have the work input, so now we can just substitute and solve for the work net. Okay, so minus, okay, this value here, minus with this value, we can solve for work net 337.77 kilojoules per kg. Alright, so next we have to calculate for the amount of heat added. Okay, so the amount of heat added, Q in total, we have already written the equation just now. Okay, is the primary, alright, plus the reheat. Okay, so for the primary, the equation we have already written it just now. Okay, Cp T3 minus T2S. Okay, so we can fill in the values. Okay, fill in the values. 524. So we can get the primary heating 853.2 kilojoules per kg. Next is the reheat. Okay, so calculate here, reheat. Okay, it's Cp T5 minus T4A. So substituting the values. Okay. T4A was 1193. So here we can get 180.9 kilojoules per kg. Okay, so let me add a new slide here. Okay. So here, so we have to calculate the total. Okay, the total. So the total heat added. Okay, so this value 853 here have to add with 180. Okay, so alright, so Q in total here. Once we have already add up the both of the heat, so we can get 1334.1 kilojoules per kg. Okay, so once we have calculated work net and also Q in, then only we can solve for thermal efficiency. Okay, so work net divided by Q in total. So work net just now was 337.77, but I just round out to 0.8. Okay, and then divide by 1034.1. So here, if I'm not mistaken, we'll get 0.327. In units percentage will be 32.7%. So this is number 1. Okay, we have solved. Number 2 is just to calculate the back work ratio, which is the work input divided by the total work output. So just now was 227.13 divided by total work output was 564.9. Okay, so here we can get 0.402. Okay, and finally the mass flow rate. Okay, so for mass flow rate we have already come up with the equation 6500 divided by the small work net, so 6500 kilowatts minus with the work net was 337.8. okay, so 337.8, so we can get here 19.24 kilograms per second. Okay, so this is a question for subtopic 5.5, Brayton cycle with reheating process. So before we leave, we forget to draw the TS diagram. Okay, so the TS diagram now. So we have here the TS diagram. Okay, so for state 1, the inlet of the compressor, we compress it to state 2. Okay, there's no isentropic efficiency, so and then the reheating the primary heating. Okay, and then we expand in the first turbine. Okay, the ideal state, and then we have the actual state 4A. Okay, so this will be the same pressure. Reheat it with the same temperature here, state 5, and then we expand it. Okay, so this is the ideal state 6S, but there is also a isentropic efficiency, and then from state 1 to state 6 we connect the rejection process. Okay, so this is the TS diagram for the question. Okay, so now we have complete the question. So thank you for your attention and have a good day.